All right. Um, shout out to Liz. I took a little bite. I have like a little protein bar, and I'm hungry. I don't know why I started recording, but I'm leaving it in. Oh yeah, I'm a human being. I eat food. The world needs to know. All right. So what do we got to do to solve this, guys? How about this? What did we do on the last one? It says solve each system by graphing. So how can I graph this? Yeah, why don't we just graph it in our graphing calculator? That's what we did on the last problem, right? So open up your handy dandy calculators. Go to y equals. Clear that out. What's the first equation? Negative 4. Oh, no, it's negative x plus 4, right? And then the next equation was just 3x, right? Is that right? Is that what you guys have in your book? Yeah. Okay. Oops. Man, who's that good-looking couple? Oh, I got to graph this. So I got them both in there. I'm going to leave the window the same, so I'm going to hit graph. Now, what does it look like the intersection is? What does that intersection look like to you guys? I'm talking about the x comma y, the point. Yeah, it's probably 1 comma 3. How can I verify that? Do you guys remember? Yeah, I'm going to hit second trace, which pulls up the calculate menu, and then what do I want? Intersect. Now this is how you solve it by graphing, and we're just letting the calculator verify that they both have that same value, and then we'll double check by hand. Okay? Does that seem about right there? Yep. First curve guess, second curve guess, actual guess. Guess what? It is the intersection. So Mr. Adams is going to take a copy of the graph, and I'm going to include that. Right here. I hear whispering. You shouldn't. I'm the only voice I should hear right now. Now, how can I prove to people that that's correct? Huh? Tell them to look at the picture. Yeah. But open the door. How about if this is the solution? You guys be serious. I know it's the end of the day, but I want you to be serious. We could say 1 comma 3 is the solution. Doesn't that mean when x equals 1, y should equal 3, correct? So I'm going to take this first equation here, and wherever there's a y, I'm going to put 3. And that should equal negative whatever x is. Wherever there's an x, I'm going to plug in 1 plus 4. Okay? So then, what is 4 minus 1? 3. Is that a true statement there? Yeah. So let's do the same thing with the second equation. I'm going to write down the second equation, and wherever there's a y, I'm going to put what value?
Negative 3.
Well, it's a positive 3, right?
Oh, yeah.
Okay. Positive 3. And then I'm going to say 3 times x, which is 1. What's 3 times 1?
3.
3. Is that true?
Yeah.
Yeah. That's it. That's all we're supposed to do. So then you would say the solution is 1 comma 3. And that's it. Does that make sense?
Yeah.
All right. Let's do part B. We're still on example 1. So now what do I do here? I do the same thing. I'm going to graph it. So what I'm going to do is I'm going to pull out my handy-dandy calculator, go to y equals, clear that out, clear this out. And I'm actually going to plug in the first equation, which is let me clear this out. Is it 3x minus 3, right? Well, I got them backwards. I'll put the other one up here. And then the other one is 3, and then in parentheses, I have x minus 1, right? Okay, double check. I know I put them in there backwards from the thing. Does that make sense? Yeah? Yeah, I don't know. So let's graph this. Are you guys ready? One will be red and the other will be blue. Ready? Watch this. Oh, what happened there? What? Let's go back again. You got to watch quick. Watch. Are there two lines there? I don't know. Let me hit three. Wait, there's blue stuff there. This is the blue graph. Do you see the blue graph? No. Why? Because it's underneath the red one. They're literally the same. So where is the intersection?
Everywhere.
Everywhere. Very good. Well, let me take a picture of that. So I have this equation and this equation. Man, I really zoomed in on this one. All right. I think I'm going to have to type some stuff here, okay? I'm going to put this here. The lines are the same. They intersect everywhere. Therefore, what did we say that was? Yeah, therefore, there are infinitely many. I'm pretty sure that there is no infinitely many solutions. So write that down somewhere. In other words, where is there a solution? Well, there is a solution here. That's a solution. There's a solution here. There's a solution here. There's one here. How many are there? Infinitely many. Does that make sense? I'll give you a second to finish writing that down. Then we got one more two reflection questions I want to answer with you guys, and then we'll finish this example. Yes. All right, let's move on to the reflection questions for example 1, and then we'll move on to the next thing. And it's almost time to go too, so it worked out perfectly. So it says a system of linear equations has infinitely many solutions. Does that mean any ordered pair on the coordinate plane is a solution? No. Only the ordered pairs that lie on the graph, I'll change that so you can see it in a second, are solutions. So what that means is, when they say any ordered pair, no. Let me show you what that means. If I go back to this, If I look at this and I say negative 3, comma 3, negative 3, comma 3 is not a solution, right? Because it's only a solution where it intersects. So when we say infinitely many solutions, that doesn't mean that everything is a solution. It just means there are so many solutions that we could choose from. There's an infinite many, but they have to be on the line. The two lines have to intersect. So negative 3, comma 3 is not a solution because it's not on the line. Does that make sense to you guys?
Yeah.
Okay, good. All right, so no, only the ordered pairs that lie on the graph are solutions. And it says, can you show algebraically that both equations in part B represent the same line? Yeah. Yeah, what do? You could pick out any point and plug it in. And so, we're going to cheat a little bit on this one. Take your calculator. And I want you, because we'd take an x value, plug it into one equation, and get a y value. If you plug that same equation into the other equation, you'll get a y value. But there's two things you could do. One is you could look at the table of values. What do you notice about that table of values? They all have the same y values, right? So you don't have to write them all down, just write a couple, right? And we know that that's true, so let's put that in there. I'm going to put that over here to the side. Okay. I'll make it a little bigger. But there's another thing you could do that's really helpful. Okay. Watch this. Be prepared to be shocked and awed. My first equation, or one of the equations, is y equals 3 times x minus 1. Hey, can I distribute that 3 through the parentheses? Yeah. So what's 3 times x? What's 3 times negative 1? Negative 3. So that equation is the same as that. What was the other equation? Y equals 3x minus 3. So you could say they are the same equation. Or I should say same graph. Because they're the same equation, they're going to be the same graph. Does that make sense? Okay. You didn't know that, huh? I know, mind blown. You're tired. It's okay. Anyways, I'll zoom out so you guys can copy all this down. And I should probably point out this is, I'm not sure if that matches up or not, but this is x, and this is, I think, y for this one, and I think this is y for this one. Now, put your calculators away, clean up your mess, and go back to your seats. No lining up at the door.